So this week we're all moving into systems of equations, and what systems of equations are really just two or more linear equations, right? And the system just talks about their common solutions. And there's three types of solutions. One of those would be if there's one solution. And so say I have a graph of one equation and a graph of another equation. The intersection of those two graphs would be my solution, right? Now, the other option that we have would be if there was no solution. So if an intersection of a graph creates my solution, my no solution would be the one time that two lines would never intersect on a graph, and that is when they are parallel. So if I have this, let's see if I could actually freehand parallel lines. That would be pretty impressive. So in the case of parallel lines, which we know are two lines that have the same slope. So if they have the same slope, those lines are parallel, and we know that they'll never have a solution. Those are the only options we have for no solution. Otherwise, if we're graphing lines, they should only have one solution, no solution, or as we see here, infinite solutions. And what that means is that, say I have this line graphed right here, right? But then I have another line that winds up graphing right on top of it. In that case, our solutions would be infinite. And what that usually looks like is when the equation of one line is a multiple of the equation of the other line. So when we solve by graphing, which is about what we're about to do, we want to see what kind of solutions we have. It says solve each system of equations below by graphing, which means that we are going to graph each equation given to us, and we're going to look for their intersections. If they have an intersection, they have one solution. If they never intersect, they have no solution. And if they sit right on top of each other, they have infinite solutions. And we're going to look at examples of that. Luckily, I don't have to create the graphs. So let's start with this first one. Notice this is in the form we want it to be in. It's in slope-intercept form, like we talked about in class. If I look at this first equation up here, at -6, I know that I'm going to have a point on the y-axis, right? Because that is my y-intercept. And from that point, I've got a slope of -5/3, right? My m equals -5/3. I can either go up 5 and -3, or I can go down 5 and +3. I think I'm going to go up 5 because look, I'm running out of room if I try and go down 5. So I'm going to go up 5 places. 1, 2, 3, 4, 5. And then I'm going to go -1, 2, 3 places. So I know my next point will be right there. Now I want some accuracy, so I'm going to bring out my ruler at this point and give it a go. Make it a little bigger. See if we can get a little accuracy with this, because what do we want? We want where these points are going to intersect. And a little bit more of a slant right there. And I'm going to draw my line. So I have graphed the first equation, right? Now let's graph the second one. We'll do this one in red so that we can see the difference between the two lines. What do we know about this one? Here, this one at y equals 5, I'm going to have a point. The next thing I know is that I have a slope. My m in this case equals 1/6. So I can go up 1 and over 1, 2, 3, 4, 5, 6. Or because it's positive, I could also go -1, 1, 2, 3, 4, 5, 6. Why can I do that? Because a negative over a negative equals a positive. Why did I do that? Because I saw where that other line was, and I knew I wanted to find where they intersected, right? So I made a call, right? I knew that it was underneath and that the negative direction was going to connect my lines. Would they have eventually connected anyways? Absolutely, right? When I draw the line, they're going to connect as long as I draw it. Let's see, right there. And when I connect these dots, right, we found the intersection of our line, right? And the solution, clearly we have one solution, right? And where's that one solution? Where these two lines intersect. And that is at, oh my gosh, I don't know, I can barely read these numbers right here. Let's see if I can make them big enough to read. This would be at -7, right? My x equals -7, and my y is 4. This would be the one solution that I have to this problem, right? One solution. What is our solution? Our solution is -7, 4, right? And that's how we solve these graphically. Let's look at this other problem right here. We have y equals 5. I don't know why I'm moving the whole piece, right? We have y equals 5. Well, what does a graph of y equals 5 look like? I talked about this, or I will talk about it for those of you who haven't had the in-class lesson yet. I apologize for losing control here. I need to keep that right there. If I have y equals 5, when I graph that, it is just a line across and intersecting 5. It's saying that for every single x, my y is going to equal 5, right? Which means that in both directions, this is just going to cross 5, right? There's no slope to this problem, right? Our slope, our m, equals 0 there. What about the other equation? Well, I have 2x plus 7, so I know that I have a y-intercept point at y equals 7, right? At 0, 7. So I'm going to go ahead and put my point there, and then I'm going to count out my other point. Well, in this one, my m equals 2, which is like saying 2 over 1, right? So every up that I go to, I go positive 1. And if I go down 2, I go -1, right? Why would I do that? Because I saw the intersection, right? And I want to make sure that it crosses that line. So let's see if we can, I could eyeball this thing and just connect them, but I'm really bad at that. So I thought I'd actually use a ruler to try and connect them, but apparently I'm really bad at that too. So we have graphed both lines, and our solution is this intersection point, right? Where is that intersection? That intersection is at -1, 5, right? My x value is -1, my y value is 5. This is my solution, right? How many solutions do I have? It is a one solution problem. Let's look at some of these other problems right here, right? I'm going to come down to question number 3. Look, I've moved my graph around so much that everything's in a weird spot. So let's go right here. If I'm looking at this, right? Let's see if I can move it here. Notice that these aren't written in our y equals mx plus b form. I am going to change that. I'm going to change it to the y equals mxb form, right? That is what we spent our time doing last week. So here I have 6x plus 5y. Just going to write the problem. 6x, minus 5y equals negative 45. And I'm going to solve this for y. I'm going to subtract 6x from both sides. And it's going to give me negative 5y equals negative 6x minus 45. I'm going to divide both sides by negative 5 because I can. And that is going to give me y equals 6 over 5x, right? It's negative 6 over negative 5, which gives me a positive. Then I have negative 45 divided by negative 5. Well, that's just plus 9. So now I know how to graph this first equation, right? It's not too bad. I know that here at 9, I'm going to have a point, and I have a slope of 6 over 5. I'm going to take them both negative. And the reason for that is I don't really have any room to go up 6 places. So I'm going to go down 1, 2, 3, 4, 5, 6, right? And then I'm going to go negative 1, 2, 3, 4, 5. The reason I had to go negative on both of them is because I need it to be a positive slope, right? We're going to bring up a ruler. We're going to connect these dots. Am I there yet? That's pretty good. Be a pro at this before long. Get rid of our ruler. Put our little arrows. We've got our first line graphed, right? My other one is also not in slope-intercept form. So I'm going to take my 2x plus 2y, and I'm going to solve 2x plus 2y equals negative 4, and we're going to solve that for y. So I'm going to subtract 2x and subtract 2x from both sides, which, sorry, I'm not trying to change that, is going to give me 2y equals negative 2x minus 4. And then I'm going to divide by 2, both sides, divide by 2. And we're going to get y equals, well, negative 2 divided by 2 is just negative 1. So we're going to have negative x. It's the same as saying negative 1x. Negative 4 divided by 2 is just negative 2. And so now I have everything I need, right? I have my y-intercept, which is negative 2. So I have a point right here. And then I have my slope, which is m equals negative 1, which is like saying negative 1 over 1. So every time I go down 1, I go over 1. Every time I go up 1, I go over 1. I could do this forever, right? This is always going to follow this diagonal. What do I know about this? At some point, they're going to intersect. I, for the life of me, don't know where they're going to intersect, but I know that at some point they will. Now, it doesn't tell me that I have to find the solution on each of these, right? It just tells me that there is a solution on each of these. Oh, well, I screwed up there, didn't I? I was acting like it was a positive, slope, but it's not, right? My slope is, negative 1 over 1. So what happens there? 1 goes up, 1 goes negative, up, negative, up, negative. That's why I wasn't finding an intersection. Am I going to find an intersection if I keep going there? Absolutely. There we go. I fixed my screw up. I didn't pay attention to the sign, and I was taking it positive. I was going +1, up 1 towards the +1, up 1 towards the +1. But it is a negative slope, so I can only turn 1. So that definitely makes our solution in this one much clearer, right? We have a solution. What is our solution? Our solution is at, what is it? 1, 2, 3, 4, 5, -5, 3. How many solutions do we have? Clearly, it only intersects in one spot, so we have one solution. This next one of our problems, right, is in the form that we need it to be in, right? I don't know why I can't get this stupid thing to move. My whiteboard froze. Let's see if I can close it and then open it again. Cool, that worked. So if we're looking at this problem right here, we can notice that one of these is already in our slope intercept form, right? We have y equals -1/2 x minus 5. If I want to graph it, it's pretty easy to graph. We have a point at -5. We can go up 1, -2. We can go up 1, -2. We could do it forever, or we could go down 1, +2, and we can also do that forever. So it makes it really easy for us to graph this problem. We're going to that should be able to do it right there. I'm going to graph this. Bam. That one's done, right? But we have this other one, this 3x plus 6y equals -12 that is not in our slope intercept form. So I'm going to go ahead and put it in there. -3x, -3x, so that I get 6y equals -3x minus 12. What happens when I divide by 6 on both sides? I get y equals -3 over 6 is -1/2 x. Minus 12 divided by 6 is -2. Look at this equation. If you notice, this one has a slope of -1/2, and this one has a slope of -1/2. What that tells me about these two lines is that they are parallel, right? Parallel lines have equal slopes, which means that they will never have a solution. We could graph it. We'd have a point right here at -2, and it's going to follow the same pattern, right? Up 1, -2, down 1, +2. And these lines will never meet, right? I didn't even have to change the angle really of my ruler. I just know that each of them have the same slope, so they will never meet. There are no solutions to this, right? Parallel lines never meet. So that's how we deal with solving things graphically, right? But we don't want to have to draw a graph for everything. So we're going to start learning how to do these algebraically. And the first thing that we do is, I would love for you to pause your video at this point, your Edpuzzle, and write down these steps for solving by substitution, right? It says solve one equation for x or y, either one of the variables. Isolate the variable. You're going to do the same variable for each equation. Substitute the resulting equation from step 1 into the equation for that variable. Solve for the remaining variable. Now, all of this sounds really crazy. And substitute your answer into step 3. Let's see what it looks like in real life. Well, if we look at this first problem number 7 here, see if I can make that a little bigger. If we're looking at problem number 7, each of these are already solved for a variable, right? They're set equal to y. So I don't have to do that first part because each of them are solved for that variable, right? This says y equals minus 7x minus 1, and this says y equals x minus 9. Well, if y equals something, that means anytime y is somewhere, I can substitute that in. So if I wanted, I could take this y equals, well, what does y equal? It equals x minus 9, and I can plug it in for y right here. What would that look like? It would look like x minus 9 equals minus 7x minus 1. And now I only have one variable to solve for, right, which is x. So I'm going to go ahead and I'm going to move these x's over to this side. Why? Because I like all my variables on the left for some reason. It's just a weird thing about me. So I have 8x minus 9 equals negative 1. Then I can move this 9 over, right? I can add 9 to both sides. Boom. And I get 8x equals, oops, sorry, I forgot my x. 8x equals minus 1 plus 9 is just 8. I'm still not solved for x, so I'm going to divide both sides by 8. And I'm going to get x equals 1. So now, for this system, I know what x equals, right? So far, x equals 1. I'm going to take this 1 and I'm going to plug it in for x in this equation, right? So if I have y equals x minus 9, right? If I have y equals x minus 9, and wherever I have x, I just plug in 1. That would be y equals 1 minus 9. Sorry, I was thinking of the answer in my head and wrote 8. 1 minus 9 is just negative 8. So our solution to this problem would be 1, negative 8. It indicates where these two would cross each other on a graph. If I were to graph both of these equations, their intersection would be at the point x equals 1, y equals negative 8. So if we look at this other problem, we have y equals negative 5x plus 30. The other one is not in slope-intercept form, but it's not all that important that it's not in slope-intercept form. I could solve this for y if I wanted, but technically I don't have to, right? Because what does it say? I have a y equals, right? What does it equal? It equals minus 5x plus 30, which means that if y equals that, where y is in this equation, I can just plug in minus 5x plus 30. So here I have 7x plus 3y. Well, that's 3 times negative 5x plus 30 equals 42. And we're going to solve for our remaining variable, right? The only variable we have is x. So we're going to solve this whole problem out and find out what x equals. I'm going to start with my distribution. So I'm just going to leave this 7x plus, well, here we've got, I don't know if that's going to be a plus in the end, right? I have 3 times negative 5x. Well, that's going to be minus 15x, right? When I multiply those two. Now I'm going to multiply 3 times this. Well, that's just plus 90. 3 times 30 is 90 equals 42. I can combine these two x's now. Now I have 7x minus 15x. Well, I know that's minus 8x plus 90 equals 42. I'm going to start undoing everything on x. So I'm going to subtract 90 from both sides, and I get minus 8x equals, what's 42 minus 90? Oh my gosh, I have no idea right off the top of my head. 42, 45 minus 90 would be, so 45 would be 45 plus 3, so it's going to be 48. That is convenient. It's going to be negative 48. The reason I say that's convenient is because I'm going to divide here by negative 8 now, and I know that it goes evenly into 48. So when I divide both sides by negative 8, this becomes x. My solution here is going to be positive, right? Because it's negative over negative, and my x value is just 6. So now we know what our x is. We have to plug it into this equation to find what our y is. So I know I have y equals minus 5x plus 30, but x is just 6 plus 30. And I can solve that pretty easily, right? This becomes negative 30, plus 30. So y just equals 0. So when I go to do this point, my solution point where these two lines intersect are going to be at x equals 6 and y equals 0. Those are the coordinates at which the graphs of these lines intersect. And I did that just by using substitution, right? Let's look at one where we actually have to solve for it. Don't worry, I'm not going to do every single one of these practice problems. But I do want to talk to you about, let's look at number 9. When I want to solve for something and I'm substituting, I'm going to look for a variable that doesn't have a coefficient in front of it because I know that coefficient is 1. So I'm not going to use one of these. I'm going to look at this. I'm going to solve this equation for y because the only thing I have to do to it is subtract 7x from both sides, and I'm left with y equals minus 7x plus 22. And that one's already solved for y. So I know that I can just plug it in for y into this equation and get an x value, right? So if I'm going to do that, let's rewrite the equation. If I have 6x minus 5y, well, where I have that y, I'm just going to plug this in, right? So y would be minus 7x plus 22 equals negative 28. And we're just going to solve this problem. So we've got 6x. I have negative 5 times negative 7x. Well, that's plus 35x, right? All I did was distribute there. Now I'm going to distribute here, and I've got 5 times 22. Oh my God, these numbers are high, right? I don't know what 5 times 22 is. I should. 5 times 20 would be 100. This is probably 110, but let's use the calculator just to check. I was right. But it's going to be negative 110 equals negative 28. And now we've done all our distribution. We can just start putting things together and solving for this x. So I have 6x plus 35x. Well, that's just 41x minus 110 equals negative 28. I'm going to go ahead and I'm going to add 110 to both sides to get rid of it, right? We're trying to clear off the x, which is going to give me 41x equals 82. Sometimes I need a calculator too. 82 is a very convenient answer. Why would it be convenient? Because I've got to divide by 41 and they go evenly into each other. And I wind up with x equals 2. So we've got our x value, which makes things really nice now, right? And we're going to plug it into our original equation, right? Which is 7x, right? So 7 times 2 plus y, which we don't know yet, equals 22. And we only have to solve it for y. So I have 14 here plus y equals 22. And I'm going to subtract 14 from both sides. And I get y equals 6, right? No, 6, 7, 8. Y equals 8. So I know, here's my x, here's my y. I know the point where they intersect is at 2, 8. So that's basically substitution. I want you to notice that you can look at these problems and know which one to solve for, right? I would solve for x in this problem. Why? Because there is no coefficient here, right? Which means all I have to do is add 7y to both sides and I can substitute. Where would I substitute it? Whatever I get over here, I'm going to substitute in for x over here, right? On this one, I would solve this equation for y. Why? Because there is no coefficient on that. This one, well, I'm going to have to think a little bit harder about, but I wouldn't even use substitution on this problem. So we could just put a big X through it. I don't want to think about it because on this one, I wouldn't use substitution. I'd use elimination, and we're not going there yet. I could, however, use substitution if I wanted. But then I'm dealing with fractions, and it's a pain. It's easier just to use elimination. So that is the lesson for this part of the week. You have a Delta Math assignment that correlates to it. If you have any questions, please, text, call, email, carrier pigeon. You know how to get a hold of me. So let me know if there's anything I can do to help. Good luck.